Started off the unit about a month ago with the cathode ray tube. And of course, with the cathode ray tube, we talked about J.J. Thomson, his model of the atom that came from that, the plum pudding model of the atom. The atom consists of a sea of positive charge with a bunch of little negative electrons floating around inside it. Well, where do we get this electron that floats around inside this sea of positive charge? It looked something like this, the cathode ray tube did, with two little electrodes. We had a cathode, we had an anode. Which one do we call the cathode? One on the left or the one on the right? The left one is the cathode, the right side is the anode. Now, prior to 1897, when Thomson did this experiment, everybody knew there was something that left this cathode, went toward the anode, went through the anode, then struck this screen, this glowing screen somewhere. Nobody knew what they were. We call them cathode rays because they left the cathode, they go toward the anode. Thomson comes along and he introduces a magnetic field down here. That caused these particles to do what? I'm sorry? Yeah, it caused the path of the particles to bend. So it's going to now look something like this. That told Thomson that we have particles, not just some mysterious electromagnetic radiation or whatever, but particles. Specifically, what kind of particles? No, negatively charged particles, right? We use our hand rule for deflection, thumb in the direction of the particles to the right, fingers field, palm points downward. So these must be negative particles. Nothing about the subatomic nature of them, though. Okay, when we talk about the subatomic nature of them, we have to go into a mathematical analysis. In this section, he said Fc is equal to Fm. Centripetal force equals the magnetic force, or mv squared over r equals qvb. Didn't know what m was, didn't know what q was. One of the v's cancels, but he didn't know what the other v was. He did know what r was, he didn't know what b was. So then he goes and he introduces another magnetic field here. That would cause the particles to deflect downwards, but he introduces at the same time an electric field that would cause the particles to be deflected upwards. For the ones going at the right speed, we know that these two forces, the upward electric force, the downward magnetic force, have to equal each other. Fe equals Fm. So we're going to say Q times E is equal to Q times V times B. Q's cancel, V is equal to E over B. Now we got another variable, V, that we can plug into here. Now all we don't have is Q and M. Rearrange this to solve for Q over M, the charge to mass ratio. That's all Thomson could do. What was special about that number? No, it was really big. Okay, it was really big. Now, if this value here that we get for Q over M is really, really big, then that must mean that M is really, really small. In fact, smaller than the mass of an atom. And if you've got a particle here, a negatively charged particle that has a mass that's smaller than the mass of an atom, then that must mean that it's subatomic. Now, this first section over here, we don't really talk about that much because we've done this a million times before back in our electricity unit. Okay. How do you think you'd analyze this first section here if you ever had to analyze that problem? How do you think you'd do it? What's the charged particle? What's the electron now that we know it's an electron? What's the electron doing as it goes from here to here? It's what? Yes, it's speeding up. It's accelerating. What do we do when a charged particle accelerates? It's like a car going, charged particle speeds up, a car is going down the hill, right? If a car is going down the hill, we'd say mgh equals 1/2 mv squared, but this time it's not really a car going down the hill. This time it's really a charged particle that's speeding up. So we're going to say q times v is equal to 1/2 mv squared there. We've done that, as I say, a million times back in our electricity unit. It's not often that you have to do that here. Okay, but occasionally it might pop up. I believe in question number 1 in your review questions that I handed out to you a few minutes ago that it actually does pop up. It's actually 146. Okay, you get this diagram of a cathode ray tube in 146. Talks about electrons being boiled off the surface of the cathode, accelerated toward the anode. Okay, you got a potential difference. You want to find the speed at which the electron hits the screen. It accelerates through the, sometimes we call it the acceleration chamber there. We'd say EI equals EF, and you're solving for this variable in question number 146 there, right? You've got Q, you've got M, And, sorry, no, you've got V as well, and you're solving for little v in that case. Make sense? Let's take a quick look at 147 while we're at it here. J.J. Thomson's experiments indicate that cathode rays are what? Photons, EMR, positively charged particles, negatively charged particles. Negatively charged particles. Man, if we get that question on a test or in an exam, we should say a little prayer of thanksgiving, because that should be a question that all of us get right. Negatively charged particles. So what are the implications of this? Hey, we got a subatomic particle. It's the first time. First time that we've got something smaller than the atom itself. The atom is divisible rather than indivisible. Next, we talked about the Millikan oil drop experiment. Okay, these two things kind of go together, although they're two completely different experiments. The Millikan oil drop experiment looked completely different, but in the end was similar in the sense that it was kind of an extension of the first one, the cathode ray tube, and found more out about the electron. Okay, we have a couple of different charges of oil droplets here, because we spray these oil droplets into this chamber between the two charged parallel plates. Some of them are positive, some of them are negative. Some of them move up, some of them move down, some of them are suspended. By the way, the top plate in this case would be positive, the bottom plate would be negative. The negative particle would experience a force of gravity down and an electric force down. This one would experience gravity down and an electric force up. Sorry, the other way around. Other way around. Yeah. Let's make this one positive and this one negative. Okay, so the negative would experience the force, the electric force upward toward the positive plate, right? And the positive would experience the electric force downward toward the negative plate. So for a particle that's suspended or traveling at a constant speed, either one of them works here, okay, which could be that negative particle, we'd say Fe equals Fg. We'd say Q times E equals M times G, and we'd solve for Q. For a particle that's accelerating, they could be this one as well, but for sure would be this one. We'd say F net is equal to Fe plus Fg, and we'd say M times A is equal to QE plus mg. And then we'd solve for Q in this case. What do we find here? What do we find when we solve for Q, a few hundred times with either of those scenarios? Charged particle accelerating or the charged particle remaining at rest. What's the pattern that you find for those charges? Brody? Yeah, they're all, sorry? Yes. You might get a charge of one oil drop that's 1.6 times 10 to the minus 19, but then you got a few hundred other oil droplets that are either 1.6 times 10 to the minus 18 or a whole number multiple of that. And that led to two conclusions that Millikan drew, two implications. Oops, made a mistake here. What's my mistake here? Shouldn't say charge to mass ratio, should it? Okay, shouldn't say charge to mass ratio. That should appear where? That's with the cathode ray tube, right? What are the implications of the oil drop experiment? Well, number one, Brody kind of already said it, we have an elementary charge. We have the smallest, we have a minimum charge that you can possibly have. Can't get smaller than that. 1.6 times 10 to the minus 19. That happens to be the charge of an electron, right? The smallest charge that you can have. The other conclusion that we draw from this is that charge is quantized, meaning that you can have this number or that number or that number, but nothing in between. My energy as I walk up the stairs on the first stair is 1,000 joules. On the second stair, it's 2,000 joules. On the third stair, it's 3,000 joules. My energy is quantized as I walk up the stairs. I can't have 1,412 joules. I can have 1,000 or 2,000, but nothing in between. Okay, the charge can be 1.6 or double that or triple that, but nothing in between. Make sense? Next, we talked about radioactivity. And this is kind of kind of a break from the cathode ray tube and the Millikan oil drop experiment where we're talking about the atom and specifically the electron within the atom. Here we're talking about nuclear decay. We're talking about one nucleus spontaneously decaying or spontaneously breaking up into some other kind of nucleus. We talk about it as a natural process, a random process, a spontaneous process whereby the nucleus does split up into something else. We've got three types of decay that we talk about. We've got alpha decay, we've got beta decay, although within beta we have two types, beta minus and beta plus. And then we have gamma decay. You guys remember what the condition for alpha decay is? Alpha and beta all come from having too many of something. Alpha decay occurs when you have too many what in the nucleus? Remember what happens in the nucleus. You've got that strong nuclear force. It's an attractive force. It pulls the nucleus together, wants to make it stable. You've got the repulsive force, the electric force, that pushes it apart. If the repulsive force wins, then it breaks apart. Well, when are you going to get a too big of a repulsive force? When you have too many protons, yes. So when you have too many protons, sometimes what happens is an alpha particle breaks off in an attempt to make the ratio of neutrons to protons a little bit better. So you have less protons. You also have less neutrons, but you have less protons, which is the important thing there. Reduces the repulsive force, reduces the attractive force as well, but not by as much as it reduces the repulsive force. Tries to make it more stable. Beta minus, that occurs when you have too many neutrons. Too many neutrons. And what happens there is a neutron changes into a proton and an electron. Remember Friday we talked about how that happens exactly via the quarks, right? Okay, the rearrangement of those fundamental particles called quarks and electrons. Neutron changed into a proton and electron. Proton stays behind. Electron gets kicked out. Beta plus decay. What is that beta plus particle, by the way? This one would be called an electron. This one would be called a positron, not a proton, a positron. That happens when you have too many, right? Too many protons, too many neutrons, too many protons. Okay, too many protons. This time, though, instead of breaking off a chunk in order to improve the balance, what we do this time is change one of the protons. Change one of the protons into a neutron, and, well, what else do we have to have in order to balance the charge? And a positron, a neutron and a positron. The positron gets kicked out, the neutron stays behind. Finally, we have gamma decay, which occurs when you have a nucleus that's left in an excited state. Okay, the nucleus is excited because something else has already happened. It doesn't want to stay there, so when it goes back down to its natural state, it gives off a photon, and that photon would be in the form of a gamma ray. Okay, nuclear decay. Mass has been lost a little bit in that reaction, okay, and it's been converted to energy. A gamma ray photon is given off. When we talk about the properties, well, properties we talked about mainly about penetrating power and ionizing power. Let's group these two together. Which one of the three had the highest, we'll go backwards this time, the highest ionizing power? Which one was number one in terms of ionizing power? Which one's the king of ionizing atoms? Alpha decay. And this one is the worst one, although it still does a pretty good job at it. In terms of penetrating power, this one's the king of penetrating matter. This one's pretty weak, actually. This one doesn't do a very good job of penetrating matter, maybe a sheet or two of paper. Now, when we talk about ionizing power, that's what kind of leads us to the effects of this radioactivity, the effects of ionizing radiation. Tell me what one of the effects on people, on cells, is because of ionizing radiation. What's one of the things that can happen? It could kill the cells, sure. Yeah. Okay, so it causes DNA damage. Okay, it can cause DNA damage. Good. Sorry? It can turn into acids? Maybe. Not sure about that one. Okay. There are chemical reactions that take place that aren't supposed to be taking place, so that's possible. I'm just not sure specifically there. But those chemical reactions can lead to all kinds of things, right? From DNA issues and reproductive issues to all the way up to cancer, all the way up to almost instant death by radiation poisoning and radiation sickness, cataracts in the eyes, okay, damage to your eyes, okay, damage to any kind of quickly reproducing cell like reproductive cells, okay, sperm and egg cells, hair cells, okay. You ever see someone get cancer treatment? What happens to them oftentimes? Hair falls out, right? Chemotherapy is chemicals. Chemotherapy is drugs, and that makes your hair fall out because the drugs are designed to attack quickly reproducing cells, which include cancer cells and include hair cells. The hair cells reproduce quickly just like cancer cells do, but radiation would do the same thing. Transmutation. Transmutation, we're changing one element to the other. We can do that by radioactivity. We can also do that by fission and fusion. The idea with transmutation is that we have to write reactions, write equations. Let's say we've got, this is the one that I always go back to because I remember uranium-235, undergoes alpha decay. It produces an alpha particle. What else? 4 plus what is 235? 231. 2 plus, that's a 9 by the way, 92. 90, and that should be thorium. Anything else there? No, stop. Don't say that. Nothing else there. Nothing else, right? If we're talking about beta decay, then there is something else in beta decay, but not in alpha decay. Let's say we've got, let's say that we've got carbon-14. Atomic number 6. It undergoes beta minus decay. 0 plus 14 equals 14, minus 1 plus 7 equals 6. That's going to be nitrogen. Anything else produced there? Yeah, we know that it's going to be an anti-neutrino. That's the little neutrino sign with the little dash above it there. If this is beta plus decay, we got to be careful here. 1 plus 5 would equal 6. Okay, not 7. 1 plus 5 would equal 6. And then that wouldn't be an anti-neutrino produced. It would be a neutrino produced in that case. Okay? Yep. And we talked about half-life. And half-life, essentially, we said was a statistical analysis, an analysis based on probability. We can't be certain about anything we do with half-life until after it's happened, because radioactivity happens when it wants to happen. But we can make pretty good predictions if we have a large enough sample size, enough radioactive nuclei, because on average, nuclei will do what they've done in the past. So in other words, on average, if half of them decay in 1,000 years, then they'll continue to do that as long as we have a big enough sample size. The half-life is the time that it takes for half of a radioactive sample to decay. The half-life can range anywhere from a small fraction of a second to thousands of years. And we have 2 equations that we use to describe half-life. First one, n is equal to t over t1 half. Okay, that's not on our data sheet. The second one, we had n is equal to n sub 0, 1 half to the little n. That is on our data sheet. N stands for the amount that we finish with. N0 is the amount that we start with, and a little n is the number of half-lives. Give me a unit that big N could be measured in, please. Could be measured in percent. If it's measured in percent, N0 is usually 100%. Okay, there are a few scenarios where it wouldn't be 100%, but it would be pretty clear to you if it wasn't. Okay, what else could it be besides percent? Could be grams. Could be kilograms. Could just be a number. Yeah, a number of nuclei. What's that one that you guys had a bit of trouble with when you had a homework question? I wouldn't worry about memorizing that. Just recognize it. Okay, you recognize it as a unit of radioactive decay. It's the number of decays per second. Indicates an amount, right? Or a megabecquerel or whatever. Anything that indicates an amount, as long as N0 has the same units. What does a little n stand for? The number of half-lives. Now, if we have to solve for little n using this equation, good, it's easy. If we have to solve for little n using this equation, what do? You can either use logs, or you can do that divide by 2 method. Little n, big N. After 0 half-lives, 1, 2, 3 half-lives, what do you got left? Well, after 0 half-lives, you got 100% left. 1 half-life, 50% left. 2 half-lives, 25%, 12.5%, and so on. Somebody asked me when we were going through this, well, when do you stop? When do you stop dividing by 2? Okay, if you're told in the question that the final amount is 50%, then you should stop after 1 half-life. If you're told in the question that the final amount is 12.5%, then you should stop after 3 half-lives. Keep dividing until you get the value of n that it's supposed to be. And do your thing. As far as the graphs that go along with this, they're always going to look the same. You're going to have n on the y-axis, t on the x-axis, and the shape of it's going to look like this. You're going to have to do one of 2 things here. What are they? What are they? If you want to find the time that it takes to get to a certain amount, you're going to go over and down and read off that time. And if you want to find out how much is left after a certain amount of time, you're going to go over and up, and you're going to read off that amount. One of the most common things that you're asked here goes back to the first thing that I just showed you. How much time does it take to get down to this amount? One of the most common things that's asked is, what's the half-life of it? What's the half-life? Well, if you want to find the half-life, go down to half of what you started with. Okay, go down to half of what you started with. This is what I started with. Go down to half of what I started with, and then go over and down. Whatever that value of t is, would be your half-life. Don't quote me on this, but I believe that question number 1 on your test on Wednesday is exactly that. What's the half-life of this based on this graph? Yeah, that should be a nice, easy one to start off with, right? The question was, guys, and we won't make it specific to page 803 there, just in general, it said find the product or something to that effect produced by the beta negative decay of whatever element, whatever random element. Okay, if we're talking about beta decay, that means a beta particle is produced. Okay, we don't call it beta decay when a beta particle is absorbed, although that can happen. We call that electron capture. It can happen. We don't call it beta decay. Beta decay is when a beta particle is produced. Alpha decay is when an alpha particle is produced. Okay, beta plus decay is when a positron is produced or given off. So when we're talking about, say, the element that's produced by beta decay, we have to make sure that that beta particle is a product. It's produced. It's a product. We don't have something that's produced on the left-hand side. We have something that's produced on the right-hand side. Okay? Mother and father on the left-hand side, kids on the right-hand side. Mother and father produce kids. So don't put a kid over here with mother and father, okay? Because the mother and father produce the kid. Okay? All right, next fission and fusion here, guys. Fission and fusion kind of goes along with radioactivity. So we'll kind of wait to draw a line here right now. It kind of goes along with radioactivity in the sense that it's transmutation. Okay, transmutation is when one element changes into another element. It can happen by radioactivity, this natural spontaneous process, or by fission or fusion, which we can make happen. Fission is when one heavy nucleus splits apart, although there is going to be a neutron on the left side as well. Okay, don't worry about that. Let's just look at the one heavy thing splitting apart into 2 lighter things. For instance, goes to, what was the example I gave in my notes? Krypton and barium, I think. Okay, there's a few examples that it could be. Bottom line is, one thing, whatever it is, splits up into 2 things, whatever it is. By the way, that number 3 isn't always a number 3, is it? Okay, it has to make sure we balance everything. Okay, that's fission. Fusion is exactly the opposite. Fusion is when we have maybe a hydrogen nucleus. I think the example that I gave you guys was heavy hydrogen. Fuses together to form helium plus an extra neutron and some energy over there. Again, it doesn't really matter about that stuff. What we care about in determining whether it's fission or fusion is this and this. two heavy things, two light things, combine together to form one light thing. Now, we also talked about chain reactions. How does a chain reaction happen in the first one? We need a neutron to be absorbed by uranium-235. How do we get more neutrons absorbed by uranium-235? Because what? Yeah, it shoots out 3 more neutrons. So if we play our cards right, then maybe those 3 neutrons can go into reacting with more uranium-235, which will cause more reactions, and so on, and so on, and so on. That maintains the chain reaction. How do we get that taking place over here in a fusion reaction? Yeah, you got to add energy to it. You got to overcome the repulsive force between the hydrogen and the hydrogen. Okay, and to do that, you need energy. But the beauty of it is that it generates a whole lot of energy. So if you steal a little bit away from the product side, then you have enough to cause the hydrogen to fuse together. Okay. If we're generating nuclear power, okay, in a nuclear power plant, which is done all over the world, including in Canada, what reaction do we use? Fission or fusion? Fission, yeah. We use fission, and we use fission because we can control it, right? We can't control nuclear fusion. Now, the issue with nuclear fission is what? Not quite as efficient as fusion, doesn't generate as much power, that's one thing. But what's the other issue with fission? The issue that we don't have with fusion. The products are radioactive, so we got to deal with those products, right? We have to deal with the radioactive waste, okay? We have to bury it. We have to provide high security, because one of those products in certain reactors, not in all of them, but in certain reactors, can be an isotope of plutonium, which can actually be used for building nuclear weapons. So if terrorists get a hold of the product of a nuclear reactor, then they've got fuel to build a nuclear weapon. Now, it's a lot harder to build it than you might think, but we still don't even want them to get the fuel for it. So we got to do something with it. This one is not an issue because the products aren't radioactive. Yep. Well, it's the energy that we can't control. In the sense that could we control the amount of fuel that we have? Sure, we can control the amount of fuel that we have. But to have a chain reaction, in order to sustain itself, okay, we have to have enough fuel to sustain that. Okay, so essentially what we're saying is, look, we don't want to run out. If we run out, well, then it stops. The nuclear reaction just stops, right? So if we have that fuel there, we can't control how quickly that reaction takes place. Okay, we can't control how much of it takes place. Okay, if we want to limit this to 2 nuclei, well, then sure, that's not going to generate enough energy to blow up anything, right? Or to melt anything. But it also doesn't do anything for us, right? So if we want to be able to do anything, then we have to have enough fuel. And if we have enough fuel, then we can't control the energy that's produced. Okay, that makes sense? Yeah, I mean, there's experiments that are being done, that have been done for years and years and years, and there's some promising things actually that may lead to being able to confine the products of nuclear fusion, this plasma that results from nuclear fusion. The kind of the most promising thing, as far as I can tell, at least, is a magnetic confinement thing. Okay, we get superheated gases of plasma, basically charged gases. Okay, and the idea is maybe we can contain this by using magnetic fields, but it's still in experimental stages, and we're still a long ways off from being able to make this a practical way of generating nuclear power. Within your lifetimes, hey, you guys are, 17, 18 years old? Wouldn't surprise me at all. Within your lifetimes, we'll be generating power by nuclear fusion. Okay. Who knows? But, I mean, there's people that spend their entire lives trying to do stuff like this, right? So wouldn't surprise me at all if they'll be able to do that on a wide scale. Before you guys are somewhere else. Okay, we talked about the chain reaction, but we also talked about the energy that's produced in both cases here. Where does the energy come from? Comes from the mass defect. which we defined in two ways. We defined as, number one, and it's not two different things. They both mean the same thing, but one leads to the other. The first way we define it as the difference in mass between the products and the reactants. So this weighs what? This weighs more or less than this. The product weighs less than the reactant. The product weighs less than the reactant. And that mass defect results in energy released. We call that the binding energy, the energy that's released in the reaction. We can find that binding energy by saying E equals mc squared. In addition, we define it as the difference in mass between the nucleus and the nucleons. So, for instance, if we took carbon-12, 6 protons, 6 neutrons, if we were to add up the mass of all 6 protons and the mass of all 6 neutrons, it would weigh different than the mass of the entire nucleus itself, the carbon-12 nucleus. Which one weighs more? The nucleons or the nucleus? Which one? No. The other way around. The nucleons. So 6 protons plus 6 neutrons has a greater mass than the carbon-12 nucleus. Okay? The difference in that mass is essentially a stored energy. And again, we call that the binding energy. Now, how do you find the energy that's released in a nuclear reaction? We did a few of those questions. And we did them, I think we did them all in the context of fission, but it works with fusion as well. Get the mass of this. Get the mass of this. Get the total mass. Get the mass of this one. What do you do with those two masses? What do you do? Subtract them. Subtract this from this. You're going to get a number that we call the mass defect. Once we have the mass defect in kilograms, we're going to find the energy, the binding energy, or the energy that's released by saying E equals mc squared. Now, if you get these in kilograms already, great. If you don't have them in kilograms, okay, get the mass defect, then convert it to kilograms, and then plug it into this equation. Okay? That's where we'll draw a line. That's kind of one more section of the unit. So we start off with the discovery of the electron and the properties of the electron and these two experiments that kind of go along with that. And then we zipped to the nucleus itself and transmutation that happens via radioactivity and happens via fission and fusion. And then we went back to models of the atom. Okay. The Thomson plum pudding model of the atom, take a break from the models of the atom, then let's go back to the models of the atom. The Rutherford experiment. You get this box of alpha particle generating material. As the alpha particles leave, they go towards this thin layer of gold foil. Most of them do what? Most of them go straight through. Most of the atom is empty space. Some of them get deflected. Like this. What does that tell us? Some of them get deflected. That must mean that some of the atom must be something in the middle that is positive, small, because most of it's empty space, but positive because it's pushing away other positive particles. And finally, a few of them do this. A few of them bounce back. That small positive thing that we call the nucleus must be heavy or dense, because if it wasn't, it would just get pushed out of the way by the alpha particle. The model of the atom that comes from that is the planetary model, small, dense, positively charged nucleus with the electrons orbiting around it. Orbiting around it anywhere we want, right? There's no rules on where they are. Then we zip to the Bohr model of the atom. 3 points to the Bohr model of the atom. But they all kind of related to the first one, right? They all kind of related to that first main, most important thing that differentiated Bohr from Rutherford. And that was what? Electrons exist on, Set levels, yes. They exist on levels. Okay, the first level, the third level, second level, the third level, and so on. They exist on levels. We always want to fill up the lower levels first. And each of those energies, or each of those levels, are characterized by a certain amount of energy. The second one, talked about this idea of stationary states. Maxwell, back we talked about electromagnetism. Maxwell said that accelerating particles generate EMR. These particles accelerate because they're going around in a circle. Watch the keys circling around my head again. Okay, we've done this demonstration 10 times by now, probably. What happens if these keys generate EMR? Well, then they're losing energy, right? They're losing kinetic energy. What happens is they lose kinetic energy. They're going to spiral in towards the nucleus like this. So the atom as we know it wouldn't exist. That doesn't happen. So these don't emit EMR for whatever reason. It's like they're not moving. They're in a stationary state. It's like they're stationary. And the third aspect, they can make transitions. They can make a jump or they can fall. When they make a jump, they have to... No, they don't generate EMR. When they jump, right, you're climbing up. You're climbing up to row 30 in the third deck of the Saddledome. You need to eat your Wheaties, right? You need to eat your breakfast because you got to have the energy. Or you need to get 15 hours sleep yesterday. You need to have lots of energy. You need to absorb energy to go to a higher level. Now, normally, that's in the form of EMR. But it could be other forms as well. Electrical energy, it could be as well. In the key book, I forget who it was. I don't think it was somebody in this class. Maybe it was. Paige, was it you? No? Somebody was asking me a question about one of the multiple choice questions in the key book. It wasn't a great question in the key book, but it wasn't terrible either. It basically came down to these electrons that were jumping levels that were absorbing energy, but it wasn't absorbing photon energy, it was absorbing electrical energy. Is that possible? Well, in the end, the electron needs energy. Does it matter where it gets it from? No. If you can give the electron a certain amount of energy, it doesn't matter where it gets it from. It's just usually in the form of photons or light. Well, when they fall to a lower level, they give off energy, and it's always going to be given off in the same type. It's going to always be a photon. Okay, when you absorb it, it can be anything, usually a photon. When it gives it off, it's always a photon. We talked about the absorption and emission spectra. Remember those three pictures? Picture them in your mind. Okay, the first one was the continuous spectrum. Okay, that was not really anything to do with atomic transition. It was just a reference diagram. We had a solid, a liquid, or a gas at high pressure. Okay. Here's our solid, hot liquid, or hot gas under high pressure. We put in a prism or diffraction grating. What do we see over here on the screen? We see a rainbow. Oh, wait a second. Not exactly in that order, or not exactly looking like that, but you get the idea, right? It's a rainbow. It's a continuous spectrum. It's not lines of one color and then another color, then another color. It's all the colors of the rainbow. Well, that was our reference diagram. The next one we introduced was a gas, a hot gas under low pressure. A low pressure hot gas. Well, it produces certain types of EMR, but not all the colors. So when we look at it, we'd still see more or less white light, just like we do when we look at the fluorescent light bulbs above us right now. If we put a prism or a diffraction grating in there, it would split up, but it wouldn't split up into the continuous spectrum. It would split up into the bright line spectrum, or the line emission spectrum. So there's all colors produced by the hot glowing solid, liquid, or gas under high pressure. There's only certain colors produced by certain transitions taking place in the gas, the hot gas at low pressure. Well, then over here we have the solid again, or the liquid, or the gas at low pressure. And get a prism, it produces all the colors of the rainbow. Okay, we got over here our screen again. What does that produce? Oh, it's going to produce our rainbow again, right? But if we introduce in here a cold gas, a cool gas, then that cool gas will now take away certain colors corresponding to photons that were absorbed by different transitions. So instead of seeing the rainbow over here, now we see the rainbow with some dark lines, some dark spots, where photons were taken away, were stolen by the cold gas, causing the gas to get warmer. Electrons to jump to higher levels. And of course, notice that if that's the same gas, that low pressure hot gas or that cold gas right there, the same gas, then our lines are going to be in the same place. They're just going to be negatives of one another, that's all. Electron level diagrams always look something like this. Notice those lines get closer and closer together. First level, second level, third level, fourth level, and so on. Over here, we'd see our energies as well. For hydrogen, the first one is negative 13.6, but it can be whatever, depending upon what element. The only thing we really have to do with that is two calculations. The energy of a transition, the frequency of a transition, the wavelength, the energy is easy. Just subtract them. The energy of level 3 minus the energy of level 1. The energy of level 1 minus the energy of level 4. Then if you want to find the frequency or the wavelength, just take that energy and set it equal to HF or HC over lambda. Remember, this energy, though, is not the energy of level 1 or of level 4. It's the energy of level 1 minus level 4, or the other way around. Next, we talked very briefly about this, the de Broglie hypothesis, or sometimes we call it the de Broglie hypothesis. It's pronounced de Broglie, but it looks like de Broglie, right? Call it whatever you want, as long as you know what I'm talking about. The de Broglie hypothesis was quite simply this. If light, which is or was thought of to be a wave, can have a particle nature, and we illustrate the particle nature of light through a couple of things, right? The photoelectric effect, the Compton effect. Okay, both of those things illustrate the particle nature of light. Well then, why can't things like electrons, particles, have a wave nature? If waves have a particle nature, then why can't particles have a wave nature? So photoelectric effect and Compton effect give us the particle nature of waves. The de Broglie hypothesis gives us the particle nature, the wave nature, I should say, of particles. Waves are associated with particles. They're intricately connected. There is a wave-particle duality of both photons, both light, okay, Compton effect, and photoelectric effect, and electrons, the de Broglie hypothesis. Now, de Broglie went so far as to actually derive an equation for the wavelength of a photon. You don't need to know that equation. If it's ever required for you, it will be given to you. Okay? You don't need to worry about that. We talked about that right now. I used to do that earlier on. I used to do the de Broglie hypothesis back in our EMR unit. But then I changed it to introduce just at the very end of the year, just before the electron cloud model, because to me it kind of goes with the electron cloud model, right? The electron cloud model says what? Electrons orbit around the nucleus, kind of like Bohr and Rutherford said they are, but they orbit around as waves, right? It's a wave function. So they don't have a particular location. If we want to look for them in a particular spot, what's the probability that we'll find them there? Well, we can, through some pretty complicated mathematics, we can predict the probability of finding the electrons in a particular spot, but it's only a probability. The most probable location would be where Bohr predicted they would be, where Bohr thought they would be. But in the end, we could find them wherever. And finally, we talked about the detection of subatomic particles. Remember, we talked about the crowd chamber and the bubble chamber. Remember, they worked in the opposite ways, right? The opposite ways. The crowd chamber, we had this gas, air, dust-free air that was super saturated with alcohol or water. Okay. Protons collide with each other. They generate these tiny little particles. We now know they're called quarks. these corks ionize molecules, and these ionized molecules cause the alcohol or the water to condense. They form a cloud. And then we follow the cloud, follow the path of the cloud. And we measure some of the properties of it based on that cloud path. The bubble chamber works exactly the opposite, right? Instead of creating clouds or condensation, we're creating bubbles. We're boiling the liquid instead of causing the gas to condense. Follow the bubbles instead of following the clouds. And then finally, what do we find? Well, I gave you that big chart, most of which you didn't have to remember. It boiled down to, we have the leptons, and we have the hadrons. The leptons, well, we had the electron, we had the neutrino, we had some other things as well. Plus we had the antiparticles. Hadrons, well, the hadrons are particles that, by the way, leptons are not mediated by the strong nuclear force. These are not affected by the strong nuclear force. The hadrons are. The hadrons, for example, we got the protons, we got the neutrons. The hadrons are made up of quarks. And the two quarks that we have to worry about are the up quark and the down quark. And then, of course, the antiparticles. Now, sometimes you're going to need the charges of these quarks. They're on your data sheet. Don't panic about them. What would the anti-up and the anti-down be like?
Yeah.
What do you mean?
Like, would they be the exact opposite, so basically like up and down, or would they be?
No, just like a proton is not a positron, an anti-up is not a down. Okay, an up quark. Sorry, let's go with the electron-proton thing for a second. Okay, an electron has the opposite charge of a proton, but that's where the similarities end. An electron is way, way lighter. Okay, it orbits around the nucleus. It has no connection to the proton whatsoever, except that they happen to have the same charge, except opposite. Okay, electrons are completely different than protons. But a positron and the electron have all the same properties. They're identical to each other, a positron and the electron, except the charge. So a positron is positive and the electron is negative. Otherwise, they're exactly the same. The mass and everything, spin, everything else about them are exactly the same. With quarks, it's the same thing. An up quark has all the same properties as an anti-up quark, except for charge. An up quark is 2/3. An anti-up quark is negative 2/3. Now, you think that's the same thing as a down quark? No, it's not. A down quark has a charge of negative 1/3. A down quark does not have the same properties other than charge of the up quark. Okay, and a down quark is completely different than an up quark, just like an electron is completely different than a proton. Okay, therefore, a positron isn't the same thing, or therefore, I should say, an anti-up is not the same thing as a down quark. Okay, the antiparticle is identical in every way to its regular particle, its matter equivalent, except for one property, which is usually charge. Yeah. Okay. One other thing that I meant to mention here, guys, with the detection of it. Okay. The reason I wanted to specifically ask you that question today is because this question will appear somewhere. I can't remember whether it's on the test on Wednesday or whether it's on the mock exam that I'm going to give you a little bit later this week, or it must be on one of those two. It's going to appear somewhere. And the question is, well, maybe it appears on the diploma as well, but I mean, I won't know that until an hour after you guys know that, right? It appears on something that I'm giving you this week. I just can't remember which one. Why do we need to get these things going so fast? We want to get these protons going so 99.99% the speed of light and smash them into each other. Why do they need so much energy? Like, why can't we just take a proton, and say, hey, you know what, break apart? Like, why do we have to smash them into each other at such incredibly high energies? Jesse? They will, yes, they will. No. Maybe not. Might not be. In fact, it probably wouldn't be on a large scale. It probably wouldn't be. Let's go back to, I gave you an analogy with a car, with two cars. If two cars collide with each other in a parking lot because they're going 6 kilometers per hour, what happens? There might be a little dent, right? But the cars are not going to smash apart, right? because there's attractive forces that act within the cars, bolts and welds and screws and nuts and everything else that provides attractive forces within the cars that keeps them together. We have to overcome those attractive forces. We also have nuclear forces acting within the nucleus that keep this nucleus together. We have to overcome that. So we have to apply a lot of energy to overcome that attractive force. Jesse said the repulsive force that acts between them. To some level, yes. Okay, because a proton will repel a proton. We have to get them close enough together, right? But that's kind of secondary because that's easier to overcome. Okay, we get them closer together. All right, good. They're close enough together to hit each other now. Now comes the work. Now we have to have enough energy to overcome that attractive force that acts within the nucleus. Okay. Yeah. Yep. Well, I wouldn't even memorize those equations. You mean in the context of the quarks? You mean? Yeah. That was meant more of. Yeah. Yes. So, proton. Well, we know that beta negative decay is a neutron changes into a proton plus an electron, right? Plus an antineutrino. Figure it out. Right? A neutron is what? Up, down, up, down. I don't remember. Let's figure it out. An up is 2/3. A down is negative 1/3. So it's going to be an up, down, down. 2/3, negative 1/3, negative 1/3. Goes to, well, the other one must be an up, down then, right? Plus, I didn't have that memorized. Literally, I just figured that out as I wrote that down. Okay, and that's what I would hope that you guys would do too. There's a lot to remember, especially if you're taking courses like social and whatever. You got tons to remember over the next 2 weeks. Okay, don't memorize anything you don't have to memorize. You figure it out, figure it out. Okay.